Good evening. It is quite an honor to get to talk to you today. Welcome to this Zoom meeting, and thanks for doing this interview. Would you go ahead and start and tell us your name and tell us about your project?
Oh, thank you for having me. Yes, my name is Dr. Arthur Hawley Compton. My project, which I published back in 1923, is all about how X rays interact with matter, a discovery that came to be known as the Compton effect. At the time, most scientists believed light and X rays were strictly continuous waves, like ripples on a pond. But during my experiments, I fired X rays at a block of graphite and noticed something strange. The scattered rays bounced off with a longer wavelength, meaning they had lost physical energy. I proved that this happens because X rays aren't just waves. They actually consist of tiny, discrete packets of energy called photons. When these photons hit the outer electrons in the carbon atoms, they collide just like billiard balls on a pool table, transferring some of their momentum to the electron.
Very interesting. What were you guys trying to do or find?
We were trying to solve a major experimental mystery that had been bugging physicists for years. Why did X rays change their wavelengths when deflected by matter? According to classical wave theory, which was widely accepted at the time, an X ray wave washing over an electron should cause the electron to vibrate and re emit light at exact same frequency and wavelength. But in the lab, the scattered rays consistently shifted to lower frequencies. They softened. I set out to measure those wavelength shifts at precise angles. My goal was to test a bold hypothesis. If we treated X rays as particles with real physical momentum and applied Albert Einstein's special relativity, could we mathematically explain where the lost energy was going?
That is so interesting. Where did the project or experiment occur?
This place took right here in the US, right in the heart of the Midwest. I conducted the experiments at the basement of the Wayman Crow Laboratory of Physics at Washington University in St. Louis, Missouri, where I was serving as the head of the physics department at the time.
What other significant events were happening around the world at that time?
Oh, so much. It was the Roaring Twenties. This was an incredible but tumultuous time in human history. We were just coming out of the shadow of the Great War. Little did we know World War II was only the prequel or the sequel. And the Roaring Twenties were kicking off in America with jazz music, new technology, and booming industry. Over in Egypt, archaeologist Howard Carter had just discovered the untouched tomb of King Tut in the late 1922s, which had the whole world fascinated with ancient history. Geopolitically, the Soviet Union had just officially formed. Germany was plunging into a devastating economic hyperinflation crisis. And in the medical world, which is near and dear to how the physics is used today, doctors in Toronto successfully treated patients with insulin for the very first time in 1922, turning diabetes from a fatal diagnosis to a treatable condition.
Wow. Who else was involved in the project?
I had many colleagues during the time. While I designed the apparatus and published the core 1923 paper independently, science is never a solo endeavor, though. Over in Europe, a brilliant Dutch physicist named Peter Debye independently worked out of the exact same mathematics for photon and scattering almost at the same exact time as I did. Because of that, sometimes you'll hear the Europeans call it the Compton-Debye effect. In my lab in St. Louis, I had a fantastic graduate student named Y.H. Wu, who taught me or helped me calibrate the equipment and ran extensive follow up experiments to prove that his scattering effect happened across all sorts of different chemical elements, not just carbon. I also owe a debt to a Canadian physicist, J.A. Gray, whose early experiments with gamma rays gave me the initial clues I needed.
What was your role in the project?
I was the principal investigator, and I wore two hats for this project: the hands on engineer and the theoretical mathematician. First, on the experimental side, I personally built and calibrated a custom Bragg X ray spectrometer. Uh, I had to painstakingly measure the intensity and wavelength of X rays scattering off graphite at exact angles, like 45, 90, 135 degrees. Second, on the theoretical side, I took Einstein's quantum ideas and derived the mathematical formula, the Compton shift formula, which is the change in wavelength equal Planck's constant divided by the electron rest mass times the speed of light, all multiplied by 1 minus the cosine of the scattering angle, which proved that energy lost by X-ray photon depends entirely on the angle at which it bounces off the electrons.
What impact did your project have on the physics community?
It caused an absolute earthquake in the scientific world. You see, for nearly 20 years, the scientific establishment had been deeply skeptical of Albert Einstein's idea that light was made of particles. They loved classical wave theory way too much. My experiment, excuse me, provided the undeniable physical proof light was real. Mechanical momentum and collides with matter like a particle. It forced the scientific community to accept wave particle duality, the idea that light acts as both a wave and a particle. This immediately inspired Louis de Broglie to propose that physical matter, like electrons, must also act like waves, which become the absolute bedrock of modern quantum mechanics. And I'm humbled to say this discovery earned me the Nobel Prize in 1927.
Congratulations. What a groundbreaking kind of find. Dr. Compton, as we conclude our interview today, could you leave us with a final thought, something motivational about the future of science and what it means for humanity?
I would be delighted to. When I look how rapidly our world is changing and how much power our discoveries put into human hands, I'm filled with hope. Actually, to quote my Nobel speech in Sweden, and that I still believe, uh, when we seek the reason for the present preeminence of our peoples, we find that it lies in great power given to us by the search for truth and its application to our daily lives. I verily believe that in the advancement of science lies the hope of our civilization. The benefits of science are not only material ones. The truth that science teachers are all common interests the world over. The language of science is universal and is powerful force in bringing the peoples of the world closer together. We're all acquainted with the sharp divisions which religious draw between peoples. In science, there is no such division. All people worship at the shrine of truth. The spirit of science knows no national or religious boundaries and is thus a powerful force for the peace of the world. So, to all the future students, scientists, and innovators out there, never stop asking questions. Never stop challenging the old dogmas. When we pursue the truth with passion and humility, we don't just understand nature better, we build a brighter, more united future for all of mankind.
I just can't thank you enough for this interview. It is an honor and a pleasure to get to sit down and talk with you. And just thank you again. I will go ahead and stop our recording and have a wonderful evening.
You as well. Thank you.